So yeah, so today I will speak about some mathematical model. You will see in terms of, I think in terms of mathematics, there's not a lot of, it's not very difficult in terms of mathematics, but it's still interesting how to build this model, how it can be used for the pandemic, and how this model has been used, for example, in for the hospital in Amiens. Okay. So before talking really about COVID-19, I will do a short history about SIR model. So I think maybe many of you have heard about the story, but maybe it's good to remind you where the SIR model come from, and also because what has been done so in the beginning of 20th century is always used today. So then most of the model used for COVID-19 are based on the same idea of the very first one. So then I will show you a model we developed. And at the end, I will just present maybe a little bit more interesting in terms of mathematics, a model taking into account the space. So let me just remind you the story of SIR model. So it starts with the plague of Bombay. So today Bombay does not, they changed the name. So now today is Mumbai in India. So and there were so plague. So the plague is also a disease transmitted to humans. So from very long time we believe that the plague was transmitted to humans by humans. But it's not true, it's transmitted by fleas. But so at the end of 19th century and beginning of 20th century, it caused a lot of deaths in India, so more than 10 million. And during that time, India was part of UK. So many British scientists work on this disease, and most of them were not mathematicians. Most of them were biologists, epidemiologists, or medical doctors, but not mathematicians. And the first one, I think, is Sir Hammer, who proposed, I think is really the main idea still used today. He proposed to divide the population in compartments. So he chose 2 compartments. He just said, so you will see again some words you heard today. Yeah. So he said, okay, you have to split the population in 2 parts. The susceptible individual, which means the individual who can become infected, and so the infected individual who are contagious. So it's split only in 2 parts. So you have these 2 groups, and the question was how you go from susceptible to infected. So it's quite easy to write the equation. You just say, okay, who are the susceptible? So who are the susceptible today? They are the susceptible from yesterday minus the one who become infected. Very simple. And who are the infected? You say so the infected today are the infected from yesterday plus this new one who become infected. So, and the question is how you become infected. So simply say to become infected, a susceptible individual has to be in contact with an infected individual. So if I translate in mathematics, what does it mean? It means S at time t plus h is equal to S at time t minus S in contact with I with some coefficient. I will explain later. So now if you put S on the left, divide by H, and put H goes to 0, you obtain the derivative, and you get this ordinary differential equation. So usually it's not written like that, but I prefer to write like this. So the first coefficient is the average number of contact, and beta is the infection rate. So what does it mean? It means, okay, S is in contact with, so you are susceptible, you are in contact with an infected, but it doesn't mean you will become infected. So there is some probability to get infected once you are in contact with an infected individual. And to get the second equation is easy. So we say what is going outside the susceptible is going inside the infected. So we have the minus that become plus. So he didn't know how to solve the system of equations. So he made another assumption. He said we will suppose that in Bombay, the population is constant. So suppose you have a constant population equal to n. So like that, you can simplify the equation. You just have to solve one ordinary differential equation, which is this one. So you find again the logistic equation. So this equation is known for a very long time. He knows that has to be solved by Bernoulli almost more than 100 years before. So he knows the solution of this equation. So now he tried to see if his model fits with the real data. So this is the real data from the plague in Bombay. So this is, so I should put only the data on it. So this is the real data, and then he put, so you are a mathematician, for you, it's easy to see that even if I don't put the solution of the equation, that his model will never follow, will never fit the real data. So you always obtain this kind of curve. Okay, so we know this is logistic equation. So, but what is important? So if I come back to the equation, so this is the equation. So he was not mathematician. So he tried many different parameters, and he never find this bell curve. So, but we know as mathematicians, so you can choose every parameter you want, positive parameter you want, and the total population is globally stable. So you will always converge to the full population. So his models say that everybody in the population will be infected. So his model is not good enough. So we should wait 20 years to have a little bit better answer coming from Kermack and Kendrik, who said you don't split the population only in 2 compartments, but in 3 compartments. So you always have the susceptible who become infected, but they add another one of remove individuals, so you recover from the infection. So, and then they do exactly the same. We do the same equation. Okay, you have the equation of Hammer, but now you have this arrow, you come for infected to recover. So now you have another coefficient, so gamma, which is the recovery rate. So now you have 3 equations, system of 3 ordinary differential equations you have to solve. And when you try to solve these equations, so it's not so magic, but you find the bell curve. So actually, if you look to the original paper, they never solved the system of differential equation. What they are doing is so they're doing kind of a linearization to find this kind of solution. So they are looking if there exists a solution of this form of the system of differential equation. So it's not a complicated exercise. So now you can prove that you can indeed prove that there exists a solution of this system which has this form. So you have, but they never solved this system of ordinary differential equation. But so today you can solve it and you put in every software you want. So it's easy to solve. But in 1927, they don't have any software. So they were looking. So if the paper is, you can find easily the original paper on the web, and you will see they are looking for this kind of solution. So what is important to see? So they are also, both of them, they are not mathematicians. They want to communicate this kind of result. So they will not communicate with the equation, but they want to communicate with the form of the solution. So in what you see, you have mainly three type of behavior. So you have one, the first one is the increasing of the number of, so this is always the number of infected, increasing of number of infected. So then you have a kind of stagnation. So it remains almost constant, or actually change the sense of variation. And then you have a third behavior, which is the decay of the number of infected. So if you don't want to communicate all of this equation, all the mathematics behind this, you need to find a simple way to communicate that. So, and here it comes the concept of infection rate. So for mathematicians, it's very easy. It's just to say, okay, if S is close to some constant, so it means if you do a linearization, so in terms of mathematics, I mean, if you do a linearization, so S star would be the equilibrium. But just to simplify maybe before, if you put S is constant, so if I come back to the equation, I put S some constant, so in the second equation, and you see you just have I times some coefficient. So what you have is just an exponential. So, but in terms of mathematics, we should say if you linearize close to a constant, I is an exponential. So, and finally, if I just want to communicate to in terms of sense of variation, I don't need to explain what is an exponential. I just need to say, I have this coefficient now. So I put some value for this guy, so this one. So I have a value, and the only thing I communicate with is the sign of R. So if it's positive, I is increasing, negative is decreasing, and if is equal to 0, it's constant. So with only the sign of the exponential, you can explain the epidemics. So this is good for a mathematician, but this is not good enough for biologists, because there is no biological meaning in this infection rate. So they change a little bit the concept to the basic reproduction number. So if I remember well, the first the one who introduced the basic reproduction number was Lotka. So the same as Lotka Voltaire. So, but it's quite easy to understand for mathematicians. So we say the growth depends on the sign of R, and we will just rewrite this R like that. So we put gamma in factor, and we have exactly the same. And then I call this guy RO. So instead of looking to the sign of small r, the only change for mathematician is just to say if r greater than 1, so the infection is increasing, r less than 1 is decreasing, and r equal 1 is constant. But this RO has a biological meaning. So if I come back to the definition of, I'm looking each term. So omega is the average number of contact. So beta is the infection rate. So I said before that gamma is the recovery rate. So 1 over gamma is, you can see that as the duration of infection. And S star, or S, is the number of susceptible. So if you try to make a sentence with all this, so you put these together, what you obtain is the average number of new infection during the infection period in a population made with only susceptible. So this is also important because sometimes we forget, we just say, oh, greater than 1, less than 1. But it means that the population is made only on susceptible. So I will come back later when I will give an example when we talk about COVID. But in terms of mathematics, so for mathematicians, if I come back to the equation, I'm looking for my equilibrium. As a mathematician, I will look for the sign of the real part of the eigenvalues. I said positive, negative. I'm looking for the sign of the eigenvalue. So instead of looking for the sign of eigenvalue, we can modify a little bit to looking if this number is greater or less than 1. So there is also another way to find RO, which is based on what we call the next generation matrix. But the idea is the same. It's just to compute the eigenvalue and look the sign of the eigenvalue. So what about COVID-19? So yeah, I'm a little bit sorry because you heard maybe too much about COVID. So I will try to be not too much pessimistic again. But let's still present some of our work. So COVID-19, so you know, so the name is coronavirus disease 2019. That's why it's called COVID. So in France, there's a lot of speech about is it oh, forget about it. If we have to say le ou la COVID, but it's not important. So the first case in France, the first official case in France is January 24. So, but now we know that this is not totally true, and we know that there's some case before, much before January actually. So in the World Health Organization declared COVID as emergency on January 30. So in most of the country in the world has implemented some lockdown or total or partial lockdown. So in France, we have a second lockdown now, which is very light actually. So, and what is the idea of of the mathematical model behind COVID-19? So there's many kind of model, many things has been developed. So people use other kind of model, but I will talk only about the SIR type model. So the first idea of most of the scientists who work on COVID-19 was to use directly the Kendrik model. So just split the population in 3 groups, 3 compartments: susceptible, infected, and remove. So you can try to do that. And so if you look for the very first paper in modeling, they use this model. And you can check, you can see there's also other paper that showing that if you use only this model, you cannot fit with what happened for real. So there is something more that should be taken into account to have a good description of COVID-19. So, and I think one of the first good idea was to, okay, so you have to describe a little bit more who are the infected individuals. So I think one of the, so there's so many papers, so I didn't read anything. I have read a lot of paper, but certainly not everything. So one of the first paper I think was very interesting. So it was in February, so very early, from Danchin and his collaborator, who was saying so that the infected, so there's not only not only one way of infection. So maybe you can so the latent is just saying, okay, you are infected, but you don't know yet that you are infected. So many the traditional way is to say, okay, you are susceptible, so become infected, but before becoming infected, you are exposed. Sometimes you'd say like exposed, which means so you are infected, but you don't know yet you are infected. So this is also the latency. So the traditional road is susceptible, latent, infected, and recover. So, but what they say, okay, for COVID-19, so if we look for the data, there is something more. So why, if you read the paper, they say, if they say if you have only one way of transmission, so they're using the data from China. So then in China, they were very strict with to control the disease. So they control the infected individual. So normally, if you control the infected individual, the disease should vanish. So they suppose very early that you have an alternative transmission road. So even if you try to control these individuals, you still have some infection. So in their model, they suppose that these two groups are contagious. So there's another paper also very early in February based on data in China. So where they give a little bit more about what is the new transmission road. So in their model, they suppose, so it's a little bit different. They suppose you are first susceptible, you are infected, but in the beginning, you don't have any symptom. And then everybody has symptoms. Some are known and some remain hidden, and both recover. And in their model also, they suppose that these one are the contagious people. So this paper is also interesting because they propose a way to simulate SIR type model when you have only partial information on the infected. So what we propose, actually, we did that on March. So what we propose is to say a little bit kind of mix of both of things. So we say that you are susceptible to become infected. So then you come in this latency period. So or latent or exposed is the same. So you are infected, but you don't know yet. So from this exposed individual, some of them will have symptoms, and some of them never present any symptoms. So we split the infected in symptomatic and asymptomatic, and then both recover. So this is what we propose, and we say all of these three compartments are the contagious individual. So, and actually it was confirmed by some paper in medicine. So they show that indeed, so you have the symptomatic who are contagious, but you are already contagious when you are exposed to the disease, and also the asymptomatics who are contagious. So yeah, and in this paper, we also give a value of the duration. So they said this is around 5 days, and this one is around 7 days. So in a sense, we were quite happy to see that what we proposed was a good one. So I think now people are using this kind of splitting. So some people add even more symptomatic levels. So in the beginning, you have few symptoms, then the symptoms are becoming more and more severe. So some people add also the hospitalization, etc., etc. But still, so once you have this diagram, it's quite easy to write the equation. So, and the idea is the same. So that's why I made this history, because so actually in this talk, as I said before, in terms of mathematics and innovative, maybe you will be a little bit disappointed, because it's not to make a demonstration of my strength is mathematics. It's just mainly this has been done and how we adapt this. So, and what we say, okay, exactly as it has been done 100 years ago, is just to say, okay, the susceptibles, the variation of susceptibles is due to an infection when you are in contact with exposed individual, symptomatic individual, and asymptomatic individual. So then like that, you can build your system saying, okay, the infected susceptible come in the latency. At the end of latency, some of them, part of them will have no symptom, asymptomatic. The other part will be symptomatic. So here we add the mortality due to the COVID. So in the rest of the equation, we didn't take into account the mortality, the intrinsic mortality. Here we take into account the mortality due to COVID, and we assume that the one who are dying from COVID as symptom, and then you recover. So you have this system of ODE to solve. So you can do a little bit of mathematics. So you can compute the basic reproduction number. So you have two ways. So you can use, as I said before, the next generation matrix, or you can compute the equilibrium. You have two equilibrium. You have only one equilibrium actually in this one. You look to the eigenvalue of the Jacobian matrix. You look to the sign, and you get this this number. So, but mainly you have three terms. So one is due to the exposed, the asymptomatic, and the symptomatic. So P is between 0 and 1. So if I come back to the definition before, so you have the average number of contact, the infection rate due to the contact with exposed individual, the duration of latency, and the proportion of susceptible. So here, this value represent the average number of new infection during the latency period caused by exposed individual. So the same, so this one is the average number of infection due to the asymptomatic, and the average number due to the symptomatic. So, and yeah, so what I was saying, so in the beginning of the infection, so in January to beginning of March, the RO was around 3. So for my computation, I have 3.1, something like that. So what does it mean? So this is important. So if you take a population made only with susceptibles, which is not true in real life, if you put one contagious individual, it will infect 3 individuals, and these 3, one will affect 3 other people. So you see, you have the exponential increasing of the epidemic. So you can do some mathematics. So finally, so you can prove, so if RO is greater than 1, the contagious individual grows exponentially. So this is important. So mainly you have to see that as a beginning of an infection. So to start an epidemic, you need that RO is greater than 1. And indeed, with that model, if RO is greater than 1, the contagious individual is increasing. And you have this exponential as the very first model. So in this model, you can do a little bit more. You can prove that for all RO greater or less than 1, you will always converge to the, so what we call disease-free equilibrium. So it means at the end, there is no more infected. So, but this is a convergence in terms of mathematics. It's not and the mathematical time is not the biological time. So the proof is quite, it's not complicated. I told you before, you made a linearization around the initial condition. So you have to solve a linear system. So this is the matrix you have. And when you look to the characteristic polynomials, so if you really want, you can compute the eigenvalue, but you don't need to compute the eigenvalue. You just what we need is just the sign of the eigenvalues. So if you look to the polynomial characteristic, you have this, and you don't need to compute A2, A1. So and what you need is to have at least one positive eigenvalue. So if RO is greater than 1, you have at least one positive eigenvalues. So you have exponential, initial exponential growth. So for the second result, so the same is not complicated if you do it well. So what I mean by do it well, so if you start by the good equation, if you start by this one, it will be complicated. But if you start by the last one, it's quite easy. So yeah, I forgot to mention that you have a global white postness, the solution are non-negative. So in particular, it means that R prime is positive, so R is increasing, and each component is smaller than the total population. So if you start by the last one, is quite easy. So you can prove that R has a limit. So then you can integrate. This has to be finite. So it means what is inside goes to 0. So there's a small trick for S and E. So you don't compute S and E separately. You make the sum, and then you have this, and it's the same. So it means this is decreasing, bounded by below, etc. So and then you integrate, you get E goes to 0 and S goes to something. So in this result, so what is important is it does not depend on RO. But again, this is a mathematical time. So this is something. So let me just show you some simulation first. So I will explain a little bit later how we fit the data. So for the moment, you can just have a look on the curve. So the dots are the real data. The gray I will explain later. So we just take a look on the curve. So we take the data, so the data are openly accessible. You can download it. Everybody has access to the data. So, but what you see is with the real data, for I will show RO later. So you have RO around 3. So you see you have an exponential increasing in the beginning. So you find again the exponential that it was proved by the theorem. So if I continue my simulation with the same parameter, I make the simulation. So what we find again is the bell curve. So exactly, so we complexify a little bit the model, but this is exactly as the original SIR model. So we find again this bell curve. So this one is made with the parameter. So we took the parameter from the first 54 days, and we continued the simulation. So it's just to say, okay, if so, there's two things. Okay, you have this exponential decay, you have the change of variation, then you have a decrease. And yeah, sorry, I should put a little bit more, but you see that you converge to the disease-free equilibrium. So, but the only say the problem with that is if you look only to the simulation, you see that so in France you will have 5 million of people infected by the disease. So in France there is a scientific committee who was making the decision. One of the members is doing the model. He's using this kind of model, not exactly this one, but he was using this kind of model to predict also the disease. But I think the most influent one was the prediction made by the Imperial College. So they use this kind of model, you can have access on, and saying, okay, if we do nothing, you will have a lot of infected in your country. So if you remember the question in March, so maybe in Portugal it was a little bit better control, but in France in February, in March, in every TV show they were talking only about how to flatten the curve. If you switch on the TV, you have someone talking about how to flatten the curve. So, and what is the answer? Why they privilege the lockdown? So if I come back again to the RO and his definition. So as mathematician, we know that RO is actually the sign of eigenvalues. So it's just a linearization. So just actually an approximation of what happened. And the model itself is also an approximation. But anyway, so if you use only the definition of the basic reproduction number, okay, you have, can be more or less more complicated as I did for expose and so on, but mainly you have 4 parameters: the number of contacts, the infection rate, the recovery, and the number of susceptibles. So here's the proportion of susceptible. So, and we say if you want to have a decay of the disease, you have to put RO less than 1. So you want to decrease RO. So you have to decrease one of these guys. So if you want to play on beta, is the infection rate is mainly about the virus itself. So you cannot do a lot of things. So about the duration of infection or the recovery, you need treatment. So just to remember you, when we start this, we were doing that on March. So on March, there are very few treatments. Some were controversial still today. So let's imagine that there is no treatment. If you want to reduce the number of susceptible, you have 2 choices. So you have to reduce the number of susceptible. You have to increase the immunity. So to increase the immunity, you have 2 choices. You can leave let the virus spread in the population. So you reduce the susceptible, or you need vaccination. So again, today, some companies have announced that they have they fund it, but still on March we had nothing. So the only thing that is remaining is the number of contacts. So if you want to reduce RO, you need to reduce the number of contacts. So you need to implement some distancing measure. So again, So the question was how you implement distancing measure in the model. So again, there's a lot of paper that was written in the same period, so we cannot say who started before, but I think most of the paper I've read, they just consider omega as a piecewise function. So they say, so omega is the number of contacts. So they put a piecewise function and they test a different value of omega. So what we did is different also because we need that the model to be well posed. So we say, okay, so you have the number of contact, and then with lockdown first. So here we take into account the lockdown. We imagine that it will be very fast, but not instantaneous. People will not accept to be locked, and also because some people will not be locked. So we first put an exponential decay of the number of contacts. So and lockdown is assuming to at the end you don't have any more contact. And then at the end of the lockdown, again, we put an exponential increasing. So when you end the lockdown, we imagine that people will go very quick to contact with other individuals. So you will come back to W omega 0, but we put a parameter in front of omega 0 saying, okay, you will not reach immediately what happened before the lockdown. So here you have the effect of the lockdown and the distancing compliance. So here, and you have this kind of curve. This is omega. So first constant, then exponential decay, and then exponential increasing. So how we get all the parameters? So first, if you look for our very first paper, so delta is the latency. So this is so 5 is the latency period and gamma the recovery. So you have 5 days to come from the latency to infected and 7 days to in the infection period. So in the very first paper we also estimate this parameter. So finally, I choose the one of this. So this is a paper in medicine. So they assume this for in Europe. So actually, when we did the simulation of the parameter estimation, we find so it means the infection is 12 days. So when I made the first simulation, I obtained 14 days in France, and in the Philippines, 15 days, because we wrote the paper with the Philippines. But okay, but for the talk, we assume that these parameters are fixed, and then you have to estimate the other parameter. So at the end you have 7 parameters. So there's something important in here is that you cannot estimate the number of contacts independently of the infection. So in other terms, the omega and beta are not identifiable separately. So this is very important because when we wrote the first paper, so one of the reviewers asked me if I can give the number of contacts. So, and I said, so with this kind of model, this is not identifiable. So this is maybe a short remark. So during this period, there were a lot of people who who did a model and put the model, and so there were a group of mathematicians and biologists who, I don't remember exactly the title of the paper. So, but they wrote a paper in Science, I think, yeah, in Science, to remind to the community what has to be done when you propose a model. So the first one they put is the identifiability. Okay, you have a model with parameter, but which of these parameters can be identified? So this is important to explain them that you can make the most complex model you want, but if you can identify nothing, is maybe not interesting. So in that case, okay, this one are not identified. And so in the second question they put is the identification, how you identify the parameter. So, and the third one is the sensitivity to the parameter. So how your output change with the change of parameter. So in this talk, I will not explain I will not show anything about the sensitivity. So if you want to, you can check on the paper. But about the identification, so the method is quite standard. So we will use a least square method. So we have access to this data. So the number of this one. So the number of infected. So we also add. So I say that I did not want to be pessimistic. So, but this is the number of deaths. So we use these two type of data to make our identification. So in the method we use is approximate Bayesian computation combined with quasi-Newton. So why is also a question. So I could cheat a little bit and choose only one trajectory which converge, which will give me a minimum. But we know when you are using a software, you can have a lot of local minimum. So approximate Bayesian means, okay, you will use a lot of paths, and then you compute the minimum, and then you select from all your paths the minimum who are in your criteria. So it means you don't have only one minimum. You have several local minimum. So there's a lot of people who are showing only one curve. So they choose the curve who is doing well. So I didn't want to do that. So I really want to show something maybe because we didn't have any idea about the COVID. So it's not so easy to select the good curve. So again, so the dots are the real data. So the red curve actually is the mean of all the stochastic of all the different pathway. So you cannot see very well, but there's also a dashed line, which is the median, but is very close to the mean. So, but it means all this gray curve satisfy my stopping criterion. So we used actually 2,000 different pathways. So, but if I really want, I can choose only one curve and plot only one curve, and I can tell you, okay, this one fit the data. But it's not too many fit the data. So, and this is typical curve, typical plot from Bayesian method. So if you are, well, you all did some statistics. So here you have the mean, and then you have the quartile. So the smaller is the box, the better is your estimation. So you can see the mortality due to COVID is very well estimated. Also, the lockdown is very well estimated. And here, so this is one of the main questions about COVID. So it's quite difficult to say what is coming from symptomatic and so is A and asymptomatic. So sometimes you can have a curve saying that most of the disease is given by. But if you look to the mean, they say most of the disease is transmitted by asymptomatics and not symptomatics. But it's P 0.4. So I forgot to say, so to make the calibration, we use the first official confirmation infection till June 16, and lockdown in France was between March 17 and May 11. So, and what happened so RO, so when, because RO actually was only for at time 0, so you can compute the R for each time. So this is what we call the effective reproduction number, but it's the same camera form. So before the lockdown, we have something a little bit bigger than 3. After the lockdown, you have this exponential decay. So I didn't put the real data, but it's very similar. So at the end of the lockdown, we were smaller than 1. So we did this paper before the end of the lockdown. So one question was, what will happen after lockdown? So we expect to the distancing compliance. So what we did, first we suppose that if you continue the lockdown, okay, no problem, you will, the epidemic will vanish. And then we look with respect to the distancing. So if most of the individual will respect the distancing, to 80%, okay, you stay way below 1, no problem. So if less and less people respect the distancing, you come greater than 1. So after this paper, so after the lockdown, we have a lot of discussion with many other mathematicians in other place than mine. And we compare our results. So I was saying that RO in France was a little bit bigger than 1.09. I was thinking some have also bigger than 1, some have less than 1, but we all have something very close to 1. So it's very important to see that when you are very close to 1, because we did, actually what we did is, again, is just a linearization, so it's approximation. So you just have to be careful about the interpretation when you are very close to 1. So, and what about the infected individual? So it's the same. So here I put the data a little bit longer because now I have the data, but we did the simulation much before that. We did the simulation just before the end of lockdown. So, and what we have is mainly, so what happened is, so if you have to compute the compliance is around 64. So this is data for France. So I didn't compute anything for other country. But what happened in France is that after the lockdown, we stayed very close to 1. And what happened this last month is that actually we are greater than 1, and the number infected increased a lot again. So now we start a second lockdown. So why this possibility? So again, if I come back to the definition, so what we have done for the moment is just to reduce the number of contacts. So at the end of the lockdown, you now open the gate, so the number of contacts is increasing, but the number of susceptible is still high. So when you open the contact, this RO will so over time, S star is kind of fuel for the disease. So if you have a lot of susceptible, nothing changes. So one question we had with the hospital. So I'm sorry because I cannot give you too much detail about that because it's work. So let me just give. So other ways to flatten the curve. So I just add this yesterday because we have a lot about we have a lot of information about vaccination. Okay, vaccination is a way to flatten the disease. So the other thing, so this is what we are doing now with actually this is also one reason why we start to do that is something we are doing with the Department of Health in the Philippines. So we are doing a model actually much more complicated. So I cannot explain. So this one I could, but okay, you have to take into account the quarantine. And there is another way. Actually, there exists treatment. So this part, so I'm working on this part with the hospital. Actually, the paper is already submitted since quite a long time now. But they asked me to that is has to be confidential. So sorry, I cannot explain the model and what is inside, but the basic idea is always the SIR, but is much more precise on what is a treatment. But I can show you the simulation just to say there's probably other way than just a lockdown. So especially in place where the distancing is quite difficult to implement. So if you quarantine only the exposed, so this is what is done in the Philippines actually. So my PhD student is now, she's Philippine and she's back to the Philippines. So when she arrived in Manila, she has to stay 2 days in quarantine to wait the result of the test. It was negative, so she was allowed to move to a place when she arrived in a, so maybe it's easier because the Philippines is made of islands, so maybe easier to to handle that. So when she arrived in a place, she has a new test. She was only exposed. Huh? She has a new test. It was negative, but she has to stay in quarantine, even if it's negative. So, but the quarantine of exposed is something very well. So again, it's deep. So what is important is the number of people you put in quarantine. So if you put in quarantine the exposed, so the same percentage, 60, 70, 80, 90% of the quarantine, you can control the disease. But you need a lot of tests and everything. So about the treatment, so I cannot give detail, but again, the treatment the hospital is proposing also allowed to reduce a lot of disease. And about the vaccine, so I just tried the vaccine. Okay, the same vaccine is also very efficient. So if you see, it's less efficient than quarantine of exposed. It's very efficient if a lot of people are vaccine. It depends really on the number of people who use the vaccine. So, but what we show is that is a treatment with efficacy of 30% is the same as 74% of compliance with distancing rule. So this is something. I think I speak maybe too much. So I will try to because it's a seminar in mathematics, so I will try to present a little bit of PG. So, but what is important, so this model has been used a lot, but don't forget this is simplified model. Also, in this kind of model, you suppose that the population is homogeneous, so you split the population compartment, but everybody is the same. So don't take into account the age, the gender, and you don't take into account the physical and social environment. So my question was to how to take into account the physical environment. So what we knew and what we know now also is that COVID is mainly a disease of contact due to contact. So my idea was very naive, is to say, okay, so if you need to take into account the contact, you need to know where is the people. So you take so you need the population density, and also what we have access is the daily transfer of individuals. So we know how many people are traveling. So from Amiens, so the one who never come in Amiens is here. So you can know how many people are traveling from Amiens to Paris every day. So from this to think, so actually this is the second step. So I propose just to take into account first the diffusion of individual. So normally you have to take or the movement of a diffusion. So you can put also the advection of this. So what I take into account is only the average of displacement of individual. So, and what I suppose is only susceptible and people who doesn't know that they are infected who are moving. So I suppose that people with symptoms will not moving. So this is just simple equation. So this is first the right reaction diffusion equation. This is the same right hand side. So it's just diffusion. So again, the diffusion coefficient will change with the lockdown. So before and after the lockdown. And this value is given. So in France, the mean daily commuting is 25 kilometers. So people many are moving to work and come back, moving a little bit, but around 25 kilometers. So you can do mathematics. So you have it's a bit more complicated, but so just UML and fixed point. You have global wide postnet. Again, you can. So this is also difficult to compute what is the basic reproduction number for PD. But still, you can have the same condition, the same basic reproduction number, and you have exactly the same type of theorem. So if RO is greater than 1, you have exponential increasing. So I have this condition more for the PD, but it's not, I think I can remove it because I wanted to do it a little bit fast. But still, you have global asymptotic stability. So almost everywhere in that case. So the proof is the same, so except so you have this PD, so I cannot do the trick of S plus I. So you multiply by E, you integrate over space, and then you have to control the sign of this guy. So that's why I put this condition. Actually, I think I don't need that. Then plus you had the Poincaré and Young's. So I will maybe not insist on the numerical way to solve the equation. So, but I use a level set method. So if you need more, so we have also access. So we don't know exactly the number of infected per city, but you have the number of infected per department. And so like that, I can build my initial map. And then just to show you the simulation. So this is so again, I did that before the end of lockdown, just to see if the model was good. So this is the simulation with lockdown. So this is the simulation if nothing was done, just the diffusion equation. So the difference is that the epidemic will invade all the country and the density is very high if you look to the data. So this one you can control the disease and also the density. So lockdown has this benefit. So and what was very interesting for me. So I did the simulation before lockdown. I did that before. I didn't want to and this is the map, the official map given by the government. So they say 1 day before the end of lockdown. So you have mainly the France in two parts. This is the most infected area and this is the good area. But it was what we simulate. Okay, so I will conclude. Yeah, I'm not so late actually. This is my 5 minutes late from the beginning. Okay, so just to conclude, so as I tried to show you that the mathematical model has been used a lot for this pandemic. So but as maybe as mathematician, we should not forget that this is always simplified model. Even the RO, which is used a lot by, so it was also one reason why I started to work on this is because I was looking on TV show and many people were talking about RO, and they didn't know what they are talking about. But as mathematician, okay, this is something very maybe very simple to use for to explain to people, but don't forget it's just linearization approximation. So what we are doing now is okay, as I said, so in this model in space, okay, I didn't put the advection part, so this is what we are doing, and what we are doing now with lab of social politics is to include also the social environment in the model. So, okay, so thank you. And if you have any question, yeah, there's the reference. Thank you.